Welcome back to the Deep Dive. Today, we're diving into the fascinating world of prime numbers through the work of Carl Sturmur, a Norwegian mathematician and astrophysicist.
Sturmur's work is particularly intriguing, I think, because it kind of bridges these seemingly, disparate fields like number theory and music.
Okay,
Yeah.
so let's break this down for our listeners.
Sure.
What exactly are smooth numbers?
Okay.
And how do they relate to Sturmer's theorem?
So smooth numbers, they're integers whose prime factors belong to like a specific set.
Okay.
So for example, like if we consider the set of primes, like 2, 3, and 5, then 30 is a smooth number because it's divisible by 2, 3, and 5.
Okay.
Right. So Sturmer's theorem states that for any given set of prime factors, there are only like a finite number of pairs of consecutive smooth numbers.
So there's a limit
Yeah.
to how many of these smooth pairs we can find,
Right.
depending on the initial set of primes.
Exactly.
Sturmer also developed a method for actually finding these pairs.
Right. That's right.
Yeah.
His method involves solving a series of Pell equations,
Okay.
which have the general form x squared minus dy squared equals 1, where d is, related to the specific set of primes we're working with.
This is where it gets interesting.
Right.
How do these Pell equations, which seem pretty abstract,
Yeah.
lead us to those smooth number pairs?
So each Pell equation, with its unique d value,
Okay.
corresponds to a specific combination of like prime factors.
Right.
By solving these equations, we can pinpoint the consecutive smooth number pairs we're looking for.
I understand this has a surprising connection to music theory.
Yes.
Particularly just intonation.
Yeah.
Could you elaborate on that for our listeners?
So in just intonation, musical intervals are represented by ratios of whole numbers.
Okay.
Smooth numbers play like a crucial role in defining these ratios, for instance, in Pythagorean tuning,
Okay.
which relies on the prime factors 2 and 3.
Right.
The only possible super particular ratios. Okay.
So those are ratios where the numerator is one more than the denominator.
Right.
Come from smooth number pairs,
Right.
like 1, 2, 2, 3, 3, 4, and 8, 9.
Okay.
These ratios give us the octave, the perfect fifth, perfect fourth, and the whole step,
Right.
which are like fundamental intervals in Western music.
So the distribution of primes essentially dictates
Kind of.
the possible harmonies within this tuning system.
Yeah.
It's fascinating how a mathematical concept like smooth numbers can have such a direct impact on music. But Sturmer's work goes beyond this, right?
Absolutely.
Yeah.
His work on smooth numbers has like broader implications
Oh, it did.
for understanding the structure of certain number fields.
Okay.
These are, algebraic structures
Right.
that generalize the concept of rational numbers.
Okay.
Sturmer's theorem provides insights into like the complexity of these number fields.
So something that starts as a seemingly simple question about consecutive smooth numbers.
Ends up having these far-reaching connections to abstract algebraic structures.
Precisely.
Wow.
And this is just one example of how Sturmer's work continues to influence like research in number theory. There's even a connection to like a recent breakthrough
Okay.
involving a tool called the Gowers norm,
Okay.
which was traditionally used to analyze randomness in functions.
That sounds like a surprising connection.
Yeah.
How did the Gowers norm, which deals with randomness, end up being applied to the study of prime numbers?
It's a fascinating development.
Yeah.
Mathematicians Ben Green and Freddie Manners,
Okay.
building on work by Green and Terence Tao, used the Gowers norm to understand the distribution of primes in arithmetic progressions.
Okay.
This work, like indirectly related to Sturmer's ideas, has opened up new avenues for research in number theory,
Okay.
demonstrating the power of like applying tools from different areas of mathematics.
So Sturmer's legacy extends beyond his specific theorem
Yes,
to influencing a whole new way of approaching problems in number theory.
that's right.
Wow.
His work has provided, valuable insights into the structure of numbers and the surprising connections between seemingly unrelated fields of mathematics.
It's fantastic.
Yeah.
It's amazing how these abstract mathematical concepts like smooth numbers can have such a like tangible impact on something like music. And to think it all stems from the work of like one individual.
Sturmer's influence on number theory is kind of multifaceted. While his theorem on smooth numbers is like a significant contribution, It's just one facet of his impact. His exploration of Pell equations,
Right.
which he used to find those smooth pairs,
Right.
has also had a lasting impact.
Could you elaborate on that for our listener? Why are Pell equations so significant in this context?
So Pell equations are a type of Diophantine equation,
Okay.
which means we're looking for integer solutions.
Okay.
They have the form x squared minus d, y squared equals 1.
What's interesting is that Sturmur's method for solving these equations,
Right.
which involves continued fractions,
Okay.
can be extended to handle other types of Diophantine equations,
Okay.
not just those related to smooth numbers.
So the techniques he developed for finding those smooth pairs have broader applications
Yeah,
in solving a wider range of mathematical problems.
exactly. For example, Sturmur's work was instrumental in partially proving Catalan's conjecture,
Oh, wow.
which is a famous problem in number theory
Right.
that deals with consecutive perfect powers. It states that the only consecutive perfect powers are 8 and 9.
So the tools he developed for one specific problem ended up having implications
Yeah.
for a completely different problem about the relationship between powers.
Right.
That's remarkable.
Yeah, it's a testament to the interconnectedness of different areas of number theory. Often, solutions in one area can illuminate and provide tools for tackling problems in seemingly unrelated areas.
And Sturmur's work beautifully exemplifies this interconnectedness.
We've been discussing the theoretical aspects of Sturmur's work.
Yes.
But I'm curious about the computational side.
Sure.
How do we actually find those smooth number pairs using his method?
So while the theory behind Sturmur's method is elegant, the actual computation can be quite intensive. It involves solving multiple Pell equations.
Yeah.
And that requires sophisticated algorithms and computational tools.
So we can't just do this by hand.
Not for anything beyond the simplest cases.
Right.
But thankfully we have algorithms and software packages that can handle these calculations efficiently.
Okay.
These tools are based on the principles of continued fractions,
Right.
which we touched on earlier.
I recall you mentioning continued fractions as a way to approximate irrational numbers. How do they relate to solving Pell equations?
So continued fractions are a way of representing numbers as a sequence of integers. What's fascinating is that the continued fraction representation of the square root of d, where d is that coefficient in our Pell equation,
Right.
reveals the solutions to the equation.
Oh, wow.
So by analyzing this continued fraction, we can extract the solutions we need.
So it's not just about brute force computation. There's a clever mathematical trick involved in finding those solutions.
Exactly. Yeah.
That's quite elegant.
It is.
Yeah.
And Sturmur's method, by connecting Pell equations to the search for smooth pairs,
Right.
leverages this elegance to solve a seemingly complex problem in a structured and systematic way.
Sturmur's theorem itself mentions that the number of smooth pairs is finite.
Yeah.
But it also provides a way to estimate an upper bound on how many pairs there can be, right?
That's right.
Yeah.
These bounds are crucial for practical computations.
Okay.
They act as a stopping criterion for our algorithms.
Okay.
If we found a number of pairs equal to the upper bound, we know we've exhausted all possibilities and can stop searching.
Right.
This saves significant computational time and resources.
So these theoretical bounds have a direct impact on the efficiency of our algorithm.
Exactly. And that's a recurring theme in mathematics.
Right.
Theoretical insights often guide and optimize practical computations. Sturmur's work beautifully exemplifies this interplay between theory and application.
It's clear that Sturmur's legacy in number theory extends far beyond his specific theorem on smooth numbers.
Yes.
His work has touched various areas of the field, from Diophantine equations to computational algorithms.
Yeah.
Is there anything else you'd like to highlight for our listener about the broader impact of his work?
So Sturmur's research has also found applications in modern cryptography and coding theory.
Wow.
While this might seem surprising at first,
No.
the underlying principles of his work, particularly the use of smooth numbers and Pell equations, have proven valuable in these fields.
Could you elaborate on that? How do these seemingly abstract concepts find application in areas like cryptography and coding theory?
So certain cryptographic systems rely on the difficulty of solving specific mathematical problems for their security. And you won't believe this, but some of these systems actually utilize smooth numbers and Pell equations
Wow.
as part of their security foundation.
So the concepts that Sturmur explored over a century ago are now being used to safeguard our online transactions and protect sensitive data.
It's remarkable, isn't it?
Yeah.
The McLeese crypto system, for example,
Okay.
relies on a special type of code based on algebraic geometry.
Okay.
And the security of this system partly depends on the difficulty of factoring certain polynomials,
Okay.
the structure of certain smooth numbers and solutions to specific Pell equations can be used to construct these codes, making them robust and secure.
So in a way, Sturmur's work contributes to the security of our digital world.
It's a fascinating and indirect connection. This exemplifies how seemingly esoteric mathematical concepts can have unexpected and profound applications in practical fields.
And it's not just cryptography.
Right.
Smooth numbers and Pell equations also appear in coding theory,
Yes.
which focuses on ensuring accurate data transmission.
That's right. They're used in designing error-correcting codes, which help detect and correct errors during data transmission, just like cryptography.
Right.
Some of these codes leverage the difficulty of solving certain mathematical problems.
Right.
And the structure of smooth numbers and solutions to Pell equations can be used to construct these error-resistant codes.
So even when data gets corrupted during transmission, these codes, which indirectly rely on Sturmur's work, can help recover the original message.
Precisely. Sturmur's work has laid the foundation for these practical applications in ways he probably couldn't have imagined.
It's truly amazing how his exploration of these mathematical concepts has had such a far-reaching impact on fields we interact with every day.
It speaks to the enduring power of mathematical ideas and their potential to shape the world around us in ways we often don't realize.
Yeah.
But despite all these advancements and applications, there are still open questions in number theory.
Oh, really?
That continue to intrigue mathematicians.
You mean after all this time, there are still mysteries about prime numbers that remain unsolved?
Absolutely. Prime numbers, despite their apparent simplicity, continue to be a source of fascination and challenge for mathematicians.
Right.
There are several famous unsolved problems related to prime numbers that have baffled mathematicians for centuries.
For example?
So one of the most famous is the twin prime conjecture.
Okay.
Twin primes are pairs of prime numbers that are only two apart, like 11 and 13 or 17 and 19.
Okay.
The conjecture states that there are infinitely many such pairs.
Okay.
While we've found numerous twin primes, we still lack a definitive proof that they continue to appear indefinitely as we explore larger numbers.
So we can't be sure that these twin prime pairs will keep popping up forever, even though all evidence suggests they will.
Precisely. It's one of the most tantalizing and enduring mysteries in number theory.
Yeah.
And it's not the only one.
Right.
Another famous unsolved problem is Goldbach's conjecture, which states that every even number greater than 2 can be written as the sum of two primes.
So, for example, 10 can be expressed as 3 plus 7.
Right.
Both primes. It sounds straightforward enough.
It does, and the conjecture has been tested for incredibly large even numbers.
Yeah.
And holds true.
Yeah.
But we still lack a rigorous mathematical proof that it holds true for all even numbers.
These open questions make the study of prime numbers even more captivating.
Absolutely.
Yeah.
They highlight the depth and complexity of number theory,
Right.
a field where even seemingly simple concepts like prime numbers can lead to profound and unsolved mysteries.
I'm curious, are there any areas of mathematics that can provide, like, tools to help solve these prime number mysteries?
Yes. One such area is analytic number theory.
Okay.
It brings the power of calculus and complex analysis to bear on the study of prime numbers and their distribution.
Calculus and complex numbers to study prime numbers. That sounds like a fascinating blend.
It is.
Yeah.
One of the key tools in analytic number theory is the Riemann-Zeta function.
Okay.
This function has a deep connection to the distribution of prime numbers.
The Riemann-Zeta function. That rings a bell.
Yeah.
It's connected to the famous Riemann hypothesis, isn't it?
You're absolutely right.
Yep.
The Riemann hypothesis is one of the biggest unsolved problems in mathematics.
Wow.
And it's all about the zeros of this function.
Okay.
The Riemann zeta function has these special points called zeros.
Okay.
And the Riemann hypothesis makes a prediction about where those zeros lie in the complex plane.
Okay, I'm trying to picture this. So we're dealing with complex numbers,
Yeah.
which have a real and an imaginary part.
Right.
And this hypothesis is about the location of these zeros within that complex plane.
Exactly. The Riemann hypothesis states that all the non-trivial zeros of the zeta function lie on a specific vertical line in the complex plane,
Right.
while some zeros are easy to find. Those are the trivial ones.
Right.
The non-trivial zeros are much more interesting.
Yeah.
And their location remains a mystery.
And why is the location of these zeros so important? What does it have to do with prime numbers?
So the location of these zeros, if proven to be as predicted by the Riemann hypothesis, would give us incredibly precise information about how prime numbers are distributed along the number line.
Wow.
It's a truly remarkable connection.
Yeah.
This abstract hypothesis about complex numbers could unlock profound secrets about the fundamental building blocks of numbers.
This deep dive is really highlighting the interconnectedness of different branches of mathematics.
Yes.
From number theory to calculus to complex analysis.
It is.
It's incredible to think that they all converge in the quest to understand these prime numbers.
It's like a grand mathematical tapestry woven together by numbers, functions, and intricate relationships.
Yeah.
And Sturmur's work, in a way, contributes to the richness of this tapestry.
Absolutely. His theorem, his method, and even the open questions his work has inspired all point to this interconnectedness.
His work on smooth numbers has provided insights into the structure of certain number fields, which have connections to analytic number theory and the Riemann zeta function.
Wow.
It's amazing to see how his seemingly specific research has had these far-reaching implications.
This deep dive has really expanded my appreciation for the beauty, depth, and interconnectedness of mathematics. What else can we learn about Sturmur and his work?
Well, we've covered a lot of ground already. But let's wrap up this deep dive by reflecting on the key takeaways from Sturmur's work and his lasting legacy in modern mathematics.
That sounds like a great way to bring everything together. What are some of the most significant insights we've gleaned from exploring Sturmur's world? As we wrap up our exploration of Carl Sturmur's work and its impact on number theory, what stand out as the most significant takeaways for you?
I think, for me, it's Sturmur's ability to connect these seemingly disparate fields, like his work on smooth numbers, which, seems purely theoretical, has these connections to music theory, astrophysics, and even modern cryptography.
It's a powerful testament to the idea that mathematics is not a collection of isolated topics, but a unified and interconnected field of study. We've also seen the enduring legacy of Sturmur's ideas.
Yes.
His theorem and method for finding smooth pairs continue to influence research in various areas of mathematics.
That's right. His work has connections to breakthroughs in prime number theory, Diophantine equations, and computational algorithms, proving that his contributions continue to shape the field.
And Sturmur's research has also found a place in modern cryptography and coding theory.
Yeah, it is.
It's surprising to see how the principles he explored, particularly smooth numbers and Pell equations, are now used to safeguard our digital world.
Yeah.
It highlights the potential of these abstract mathematical concepts to have, like, unexpected and significant real-world application.
Exactly. His work on smooth numbers, seemingly theoretical, has had these far-reaching implications, showcasing the power of mathematical ideas.
And despite all these advancements and applications inspired by his work, there are still open questions in number theory that fascinate mathematicians.
Right. Prime numbers, despite their seeming simplicity, continue to be a source of intrigue and challenge.
The twin prime conjecture and Goldbach's conjecture, for example, still elude definitive proof.
Yes.
Reminding us of the depth and complexity of number theory.
Absolutely.
It's remarkable how various branches of mathematics converge in the pursuit of understanding prime numbers, and ultimately the structure of numbers themselves. It's been a fascinating journey exploring the world of Carl Sturmur and prime numbers.
Indeed. From seemingly simple concepts like smooth numbers to intricate connections with various fields, Sturmur's work has offered us a glimpse into the beauty and complexity of number theory.
That's our deep dive into the world of Sturmur and prime numbers.
Yes.
We've seen how a fascination with seemingly simple mathematical objects can lead to profound discoveries and inspire generations of mathematicians. Keep exploring, and you never know what mathematical wonders you might uncover. Until next time.